Hi everyone. In this video, we are going to divide the nodes of a given graph into two communities using a brute force approach. Now, brute force approach means we will be trying all possible divisions of the nodes of the graph into two parts, and after that we will check which of these divisions is the best. Now, how do we check which of these divisions is the best? As per the definition of communities, the nodes which are a part of a community, they form a lot of connections to the nodes of the same community, and they form very less connections with the nodes of the other communities. So we are going to make use of this property, and we are going to find the best division out of all possible divisions, and that is what we will display. So let's get started. So let me import network X. So let me create a function here. Let's pass the graph here. Okay, so we are given the graph object. Our aim is to divide the nodes of this graph into two partitions. So let's first get the nodes of this graph. So we can make use of this function g dot nodes. You might be knowing that this returns a list of the nodes of the graph, and let's also check the total number of nodes. So we can write g dot number of nodes. Now our aim is to divide the nodes of this graph into two communities. Let's call them first community and second community now on. So we have to divide the nodes, this list of nodes, into first community and second community. Since we have to try all possible cases, we would have to try all those cases where the first community has one node and the second community has n minus 1 nodes. All those cases where the first community has has two nodes and the second community has n minus 2 nodes, and all those cases where the first community has 3 nodes and second community has n minus 3 nodes, and so on. So we have to check for all these possible cases. So if we find the combination of nodes that are going to fall in the first community, it's very easy to get the nodes which are going to fall in the second community, because they are going to be all the remaining nodes. So our aim is to get all the nodes that may fall into the first community, basically all the combinations of the nodes that may fall in the first community. So how do we do that? In order to get the combinations, there is a function in the package called intra tools. So I'm going to import that package, and the function name is combinations. Let me show you the functionality of this function first. So let me show you on IPython console how this function works. Let me import iter tools here, and let me show you the functioning of the combinations function, iter tools dot combinations. So we pass two parameters in this function. First is the list from which we want the combinations, and second is some number that we pass, which goes from 1 to the length of the list. So length of the list is 4 here, so we can pass any number from 1 to 4 here. Let me pass 2 over here. So what it does is it returns all possible combinations out of this list which are of length 2. So let me run this. This another point to note here is that this function doesn't return a list, it returns an object which has tuples of the combinations, as in the combinations are in the form of tuples. So if we want to see that, we will write, maybe we can use a for loop for I in, let me use this. Okay, for I in this object, print I. So it has returned the combinations in the form of tuples. Since we are working in list, we would want to convert them into list, so we can do that by just writing list over here. So now it is returning in the form of list. Similarly, if you want all the combinations which are of length 3, then you will write like this. So our aim here is to get all possible combinations of the nodes list which are of length 1, 2, 3 and so on. So let's get back here. We are going to put all the combinations in a list. So let me create a list first. Say first community. Okay. Now I'm going to start a loop for I in range 1 to what is the length of our list? That is n. So I'll write n by 2 plus 1. I'll explain why I did this. So I'll store these combinations that this function will return in the form of a list. And also, since it returns tuples, I'll first convert them into a list. So I'll write list of x for x in whatever it returns. Okay. Let me also pass the parameters. So the parameters are going to be the nodes list and I. So as you can see, the I is ranging from 1 up to n by 2 plus 1. So why did we do n by 2 here? This is because the cases where the first community has k nodes and the second community has the remaining n minus k nodes, and the cases where the first community has n minus k nodes and the second community has k nodes. So these cases are going to be exactly the same. These divisions are basically the same. So there's no point of checking all the 1 to n for the first community combinations. So that's why we are starting from 1 and we are stopping at n by 2. That is, if the list nodes list has 10 elements, so we'll start from 1 2 3 4 up to 5, and we are not going to check for 6 7 8 up to 10 cases. This is because they are going to give us the same divisions, and there's no point checking for the extra cases. And the reason why we put plus 1 here is that you might be knowing the functionality of this range function. If you pass 1 comma n in range, it goes from 1 to n minus 1. So since we want it to go exactly up to n by 2, we are going to add plus 1 over here. So what is this com variable going to have? This is basically going to have a list. This com is a list of lists where all the lists are having elements I elements. So as I showed you on the screen, com is going to have all these all these 4 lists for the value 3, and for the value 2 it is going to have all these lists. And after this, our aim is to add all these combinations to this list first community. So what I'm going to do here is first community dot extend, and I'm going to add all the lists that I'm getting from this com list. Now let me tell you why I'm using this extend function here and not the append function. Let me show you on over here why I used extend. Let me take some example lists. Let me take another list and yet another list. So if I do L1 dot append L2, what will happen? Let me print L1. See how it is adding the elements. My aim was basically to add this 3 4 to this list which is having 1 2 already. So when I write L1 dot append L2, where L2 is itself a list, this is how it does. In case I want to add only the elements, we make use of the function extend. So let me show you L2 dot extend L3. So let me print L2. Now this is how it works, and this is how I want it to be. That is why I have used this function extend. This is because com is a list of list, and I want to add the elements only to this first community. So we are using extend function here. Now we have stored all possible combinations of nodes in this list first community. Now we should also do the same for the second community. So I'm going to create a list here. Now this is going to be very easy because all the remaining nodes are going to fall into this community. Now you see we have the list of all the nodes. We have the list of nodes which are going to fall in the first community. We have to get the list of remaining nodes in the second community. So how do we do that? So basically we have to subtract the elements of first community from the elements in nodes. So how do we do subtraction in list? If you want to do subtraction, set is the appropriate data structure. So what we can do is we can convert the list into set, and after that we can apply the subtraction operation. For example, I can write set nodes minus set first community. So whatever it will give me the difference of the elements from nodes minus first community. It will give me the difference of elements, and that will also be in the form of set, so I can later convert them into a list. So that is how I will get the second community lists. So let me store it here. Now since we have to do it for all the elements of first community, we have to start a loop here. So I'll write for I in range. So I'm going to do it for all the elements of first community. So I'll write length of first community. Alright, so we are going to do it for all the elements of the first community, and once we get the list in L, we have to append it to the second community list. So I'll write second community dot append L. So now we have all the combinations in this list first community and all the combinations of the second community in this list second community. And please note that these two lists are themselves lists of lists. So we have the divisions in these lists, and we have to find which division is the best. Now as I told you, as per the definition of communities, the nodes which are a part of one community have a lot of connections with the nodes in the same community. That is, there are going to be a lot of intra community edges, and there are going to be very less inter community edges. So if a division is good, then the number of intra community edges should be high and the number of inter community edges should be less. So this is what we are going to use here. So we are going to keep track of the number of intra and inter community edges for all the possible divisions that we have made so far. So what we are going to do now is which division is the best. So this is what we are going to check now. Since we have to keep a track of the number of intra community edges in the first community, we will create a list for it. And we have to keep a track of intra-community edges in the second community. We'll create a list for it, and we also have to keep track of the number of inter-community edges. So we have these three lists. Now apart from this, to check which division is the best, we are going to find a ratio where in the numerator we'll have the sum of intra-community edges, and in the denominator we'll have the inter-community edges. So whichever division has highest value of this ratio will mean that in that community, inside community there are dense connections and outside community there are sparse connections. So we are going to find this ratio for every division that we have made so far. So I am going to create this list as well. Let me write here what this means. Ratio of intra divided by this is basically number of intra and number of inter community edges. Okay, all right. Now we have the nodes which are falling into the first community and the nodes which are falling to the second community. Our aim is to find the number of edges that are existing amongst the nodes in the first community and the same for the second community as well. Now, how do we find the number of edges amongst the nodes in a given community? Because we have only, as of now, we have only the list of nodes. So for this purpose, we are going to make use of a function that is subgraph, which is given, which is inside the graph object. So we'll make use of the subgraph function. Let me tell you the syntax for this function. So this function is available in graph object. So I'll write g dot subgraph, and here I can pass the list of the nodes. So in our case, the lists of nodes are kept in first community and second community also. So firstly we are doing for the first community, and for the first community also let's do it for I. We are going to start a loop here for I in range. Basically whatever we are doing, we have to do it for all the lists given in the first community. So we'll start it for I in range. We'll write length of first community. Yeah, so I was telling you about this subgraph function. This function basically takes as input a list of edges and it returns a graph object itself, which is an induced subgraph over this list of elements, over this list of nodes. So the whatever it returns is basically a graph, and whatever operations you can apply on graph, you can apply on the returned value of this function as well. So if we want to find the number of edges, we can just use the formula that is number of edges. Since this is itself a graph object, as I told you, subgraph returns an induced subgraph, which is a sort of graph itself. So you can apply this function number of edges on the returned value. Now whatever it returns, we have to store that value in this list, which is number of intra edges, because this will give us the number of intra edges in that subgraph. So I'll write number of intra edges in first community dot append. All right, so let me explain you once again what this statement is doing. So we have the nodes that are falling into the first community, and these are here first community I, right? We are starting this for loop from I goes from 0 to the length of the first community. Basically we are checking it for all the possible combinations. So we have this list of nodes which we are passing into this subgraph function, which so this function will return an object of graph itself. So that will basically be an induced subgraph over these nodes. So since that is a graph, we are calling this function number of edges to find the number of edges which are existing amongst those nodes. For example, if we pass 1, 2, 3 here, this will tell us the number of edges amongst these 1, 2 and 3 nodes. If there is an edge from 3 to 4, let's say, that will not be counted here. That's because 4 is not a part of this subgraph. So that's how we'll get the number of edges, and that information we are storing in this list. As you know, we created this list, number of intra edges 1, that is for first community. So we are appending that information here. Now the same thing we have to do for the second community as well. So we are just going to copy paste it, and I'm going to write second community here, and the information has to go to this second list, and here I'll write second. Yeah, I think we're done. So now we have the number of intra edges in the first community in this list, and we have the number of intra edges in the second community in this list. Now we have to find the number of inter edges. So we can easily find the total number of edges in the graph, right? Let's do that. E is equal to g dot number of edges, right? So we got the total number of edges here, and we have the intra edges in first community, and we have the intra edges in the second community. So if we subtract all these intra edges from the total number of edges, we will get the number of inter edges, inter community edges. So let's do that. So what we'll do is E minus number of intra edges in first community, we're going to start a loop now, minus number of intra edges in the second community. Okay, and we have to do it for all values of I. So I'll start for I in range. Length of, here we can use length of first community or second community because they are the same. So number of intra edges, or to maintain uniformity I'll write first community itself here. So okay, we have to keep this information in this list, that is number of inter edges. So I'll write it here. I'm sorry. So in this list, number of inter edges dot append. So we have to append this information here. So now we have the number of intra edges in this list, we have the number of intra edges in the second community in this list, we have the number of inter edges in this list. Next thing is to find is the ratio. So let's find the ratio. Okay, so again we have to start this loop. I'm going to copy here. Sorry. Okay, so we have to find the ratio for all these possible combinations. Ratio is going to be the division of number of intra edges with the number of inter edges. So numerator is going to be the total number of intra edges. We have intra edges in two lists, so we are going to sum them up, the values from this list plus the values from this list. So I'll write number of intra edges 1 for the ith combination plus number of intra edges in 2 for the ith combination. So we have to sum them up, and then we have to divide them with the number of inter edges for the ith combination. So since I want all the precise values, I'll write float here, and this will give me the ratio, and this ratio I'm going to keep in the list that I've already created by the name ratio. So I'll write ratio dot append. Okay, so let me explain you once again what this statement is doing. We are finding the ratio of the intra and inter edges. So in the numerator we have the total number of intra edges, and in the denominator we have the total number of inter edges, and this ratio we are just keeping in this list which is named ratio, and we have already created that list. Okay, now we have all the ratios in this ratio list, and our aim is to find the list the best value of this ratio, that is the maximum value of this ratio. So what we can do is, so let's create a variable, max value is equal to, so this is a function that we can use, max function, and the parameter can be the list. This returns us the maximum value in the list ratio. Now our aim is not to get the maximum value, basically our aim is to get the index at which the maximum value is coming, so that we get to know what was the best division. We can make use of the index function from the list, that is ratio. So what we can write is ratio dot index max value. So what it will return is, it will return the index of the max value here. So I'll write max index is equal to ratio dot index. So this index is what we are interested in. This is because this index tells us the division which is the best division out of all possible divisions. So now we got this max division I'm sorry, max index, that is the best index. And in the first community and in the second community list, we have the divisions of nodes into first and second community. So we are going to access the division out of this list and out of this list which is falling at this index. So what we are going to do is we are going to basically print the final result. So I'll write first community and which element, the one which is falling at max index, and similarly second community we're going to access the element which is falling at max index. Now I'm going to print these. So okay, let me just do some representation thing here. So after this is done, I'll I'll add a bracket here, and then I'll start the other one, and this, and then I'll close it. Okay, this is about the representation. So this is how our lists, two divisions will be printed, divisions of nodes into two communities. Now the function is written, we have to now call it and use it. We want an example graph here. So let me take an example graph here. Okay, the function name is communities fruit. So let me call this and let me pass this graph as an example graph. Let's take a graph which is called barbell graph. I'm going to show you what this graph looks like, and let's pass two parameters here. So let me go back to the IPython screen, and I'll show you how this graph looks like. So let's go here. Let me import the package networkx, and I'll show you how this graph looks like. So I'll take a graph g is equal to nx dot barbell graph, and I'm going to pass the same parameters. Now what it indicates, I'll show you in the visualization. So I'll write nx dot draw. In order to show this, I need matplotlib, so I'll import matplotlib dot pyplot as plt, and I'll write plt dot show. Okay, now this is the graph that comes out of these two parameters 5 and 0. So let me explain you what these parameters indicate. The first parameter, which is 5 here, it indicates that there should be two clicks of size 5, as you can see here, first click and the second click, and they should be connected by a path which has these nodes, which is 0 node here. So this is the path which is connecting these two clicks, and it has 0 node. So this is how it looks like. Let me change the parameters a bit and show you how it comes out to be. So if I pass 4 and 1, let's see how it looks like. Okay, so we passed 4 comma 1, which means there should be two clicks of size 4, as you can see, and they should be connected with the path which has one node. So the same is showing here. So this is one node in between. So this is the kind of barbell graph. I plan to take this graph because the kinds of communities are quite visible here, and it's also small, so it won't take much time for the testing. So I'm going to take this graph. So let's go and test this function. Okay, this is, yeah. So these are the two communities that we get. If you remember, we passed 5 comma 0, which means 5 plus 5, there are going to be 10 nodes, and these 10 nodes are divided into two communities, where the first community has 0 1 2 3 4 and the second has 8 9 5 6 7. Let me quickly show you once again what kind of plot we were getting when we passed these parameters. Okay, see, this is what we got. So here you can see that communities are clearly visible, that these should be the communities, and our brute force algorithm is nicely able to differentiate the communities. So as you see, 0 1 2 3 4 5 are falling to one community, and the rest are in the second one. So that's what we are getting here. So the brute force algorithm is working fine. Next we are going to see the Girvan-Newman algorithm for community detection.